Hey, this is Chris. I'm back again, just wanting to demonstrate quickly how to add some new capabilities to the ZXN compiler. Today, we're going to add the SizeOf operator. This operator can return the size of either a data type. So in this example here, we see we've got the data type DT, which is defined as a struct with one int and a byte. So we expect that to be 3 bytes big. Ints in ZXN are 2-byte integers. Also have an instance of that DT struct called data. And we want to look at the size of that as well. Then we have a 20-byte array and an array of 20 ints. We want to see what those size is. But also in this example, just pass an explicit data type, more complex than just the example DT here, where it's an array of bytes, and make sure that that works. So that's what we want to achieve today. Let's get started. The first thing to do, because it's going to be a new keyword in the compiler, we'll actually create a token for it. And let's find the best place to put this in. I think it's going to be, have an address option. So let's do it around there. That's probably similar. SizeOf, right? So we've defined our new token type. We're going to emit from the scanner, right? Now we want our scanner to recognize that, let's see, there's address, right? When I recognize the keyword SizeOf, so when our scanner encounters that, it's going to emit a token of type SizeOf. Right, so that's our scanner done. It will recognize the SizeOf keyword and emit the right data type. The next step is to actually handle that in the parser. So when we encounter those data types, we need to parse it and emit our abstract syntax tree nodes. Fortunately, SizeOf is going to be pretty easy. We only use SizeOf in expressions, so it's always going to be the right-hand side. And if you have a look here, in this case, it's println and an expression. So expect a constant expression for all of these. That's the other key thing, it'll be constant. Our data types don't change their size dynamically, at least not in ZXN. Right. So we will add this into our expression parser. Now, our expression parser is a recursive descent parser, and the very lowest level, the highest precedence, is parse factor. That's enough to get us there. And parse factor is a thing that handles, obviously, bracketed expressions, but all of our literals, if I come across an integer, the float, function calls, our built-in functions, they're all handled at this very lowest level, and SizeOf will be the same. Now, typically, I will create a parser function that will get called from here. But today, just to keep this simple, and we don't have to put you through the pain of watching me type, I will just implement the code here. It's not going to be too much, right? So now if our parser receives a token type SizeOf as part of the expression, we will start parsing it. First thing we'll do is we'll skip over the current token, which is the token representing SizeOf. Right? And I'd just like to put a comment here that tells me what I'm skipping over. It helps when I'm in the debugger and I need to know what where I am in the context of the source code. Right, so we've skipped that token and now expect an open parenthesis, right? We have a look at this, it's SizeOf, in all cases, followed by an open parenthesis. I have a parser helper function that I've written that says, hey, I'm expecting a token type lparen, and I will, if I don't see that token type, the error that I want to raise is going to be an expected error, telling you that this is what was expected there. We've got something else, and that should cover us. Yeah, and for the error checking, and then once we've skipped that, I now have an interesting dilemma. I have two different things I want to check for. In one case, it's an explicit data type. In another case, it's actually an expression, and I obviously want to get the data type, the resulting type of that expression, and return the size of that. So fortunately, I have a utility function in my type system that can tell me if the current token, or the token I parse it rather, which in this case will be the current token, that's the token after the lparen, is a data type or not. And if it is, we'll parse that data type in its entirety. And if we look at the signature for parse data type, it returns a type spec. We'll install that somewhere. So let's just create a type spec variable here. And say type. So now we'll have the type, the data type. Now, type spec is a base class that represents all of my types in the system, and it has a handy feature called size that will tell me how large that data type is. So we're going to use that a little bit later. Otherwise, if it's not a data type, then we'll assume it's an expression, because that's all the only other thing we're going to expect here. If it's not, then we'll compile all error out. So we'll say parse expression, right? And our expression returns an expression AST node, and all the AST nodes carry the type information with them. So we're going to be able to leverage that and say type is equal to. So in both cases, whether it's an explicit data type or an expression, we now have our type returned to us. And I can now say I've parsed that. I expect clothing parenthesis after that. So let's check for that quickly. Token type, which will be a right paren. And we'll return errors. Same thing expected. Right, okay. Let's get some space on the screen here. Now, the expression, you can see parse factory returns an expression variable, so I can just initialize that. This is going to be a constant expression, and it's the new AST node that we want to add to the tree. The new int AST, it's going to be an integer node. Got 3 overloads here, and the one I'm going to use now is going to be a version that takes a token. Right? Let's just make sure that at any point in time we can tie an AST node back to the original token that generated it. What value do we want to put in here? That's going to be nice and easy. We've got our type, and specifically we want the size for that. Now, what data type does this int AST node represent? Int AST is a little bit generic. It can actually represent bytes, signed or unsigned, integers, signed, unsigned, etc. So I've got to tell it that in this particular case, this node is representing a uint. Let's go for uint 16. Right? We don't have negative sizes. And that will be the expression. We'll add our break. If all goes according to plan, that should do the trick. Let's build this. Compiler builds. Right now, when I execute the compiler, it's set up in debug mode to always compile this test.zxn. So I'll run this. Let's see if we get any errors. No errors. So this code that I wrote successfully parsed and compiled. Let's see what it generated. Zoom in a bit on this code for you. Okay, let's get started here. We'll move this over. We can correlate it with the original source code. Right, if we have a look at this first piece here, line 11, you can see the comments emitted into the code that's generated. So for line 11, this was the code that was emitted. We loaded HL with 3, which is in fact the size of DT, the 2-byte int and the single byte. That's 3, and we print it out with the new line. Then we have uint 3 for line 12, and that's correct. It's the instance of that data type, that structure. Right? Also 3. Then we have the size of bytes, which is our array of 20 bytes. It's 20. Size of ints, which is our array of 20 integers, it's size 40. And then finally on line 15, we have our 12-byte array, size 12. Make a little change here. Change that to int. Right. Build the compiler. Run that. And there we see 12 integers, 24 bytes. Okay. So now the compiler handles SizeOf. I do need to do a little bit of cleanup, maybe add a bit of extra error handling, but for the most part, that's it. I hope you found that interesting, And if you're interested in seeing more about the compiler, let me know. You'll have a good day. Thank you. Bye.